This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over titrations, including monoprotic titrations, the common titration curves, and a polyprotic titration. We use titrations whenever we have a solution that has a compound, and we know what the compound is, but there's an unknown amount or concentration of that compound. So for acid-base problems, you're going to have some unknown concentration of an acid or base, and then what you do is you react that with the opposite. So if you have an unknown concentration of an acid, you react it with a solution of a base, but you know the concentration of that solution with the base, and then you're able to tell, based on how much of the base we added, how much of the acid was present in that solution. So here is a typical question that they may ask you on the test, and this is a really straightforward one to solve, but what we're going to do is break down this titration curve at every point, because you need to be able to just think really fluidly about a titration curve and think about each of the parts of it. So starting at the very beginning of the curve is the easiest place to start with, and at this point all we have is our acid in solution. So this curve is representing the pH of the solution with the unknown concentration of the acid. So we have HA here to represent our acid, and at point 1 we have a weak acid in solution. So in order to find the pH of this, you would set it up like a normal weak acid problem, which is what we have written next to that number 1. And so the way you would solve this would be using the ICE table. And we're not going to go through that because we've done that in a previous video. Past point 1, we start to add the sodium hydroxide as stated in the problem, which, remember, that is NaOH. So the Na and the OH dissociate to where we're pretty much just adding OH. So now our equation becomes HA plus OH, because for every OH that gets added, it is taking a hydrogen from that weak acid. Because remember, in the beginning, the weak acid barely dissociates at all. So whenever we add the OH, it just takes that another hydrogen from a weak acid that has not dissociated, and it creates H2O. So the hydroxide ion that gets added is pretty much just negated, and it turns into water, and we are left with a conjugate base from the original weak acid. And that range would run about from just right past point 1 to about over here, and we'll talk about what happens after that second line, but that entire area here is point 2. Now you want to think about, how do you calculate the pH during this point? And remember that in the original number 1, barely any of the HA had dissociated because it's a weak acid. So that means that there was not a lot of conjugate base. And so something like the Henderson-Hasselbalch equation is worthless here because there's not a lot of conjugate base. And that's why we just did the ICE table. Now when you get to number 2, you would have a lot of the conjugate base because now you're adding substantial amounts of OH. So you're having substantial amounts of HA turning into A-. So during the point from which we are adding NaOH, we start using the Henderson-Hasselbalch equation to calculate the pH. Now notice how towards the end of point 2, our curve is starting to go up a lot. And what that is telling us is that we are running out of HA. We almost don't have any HA left. So whenever we keep adding OH, there's nothing for it to react with. So at this point, we have now reached point 3. And point 3 will start at that dot, and it continues on for the rest of the titration. And point 3 will be this reaction here, where there is no longer any HA to react with the OH because it's all been used up. So whenever we add the NaOH, it just dissociates, and all it is doing now is increasing the concentration of OH. As we add OH, that's going to be the main contributor to the pH whenever we get past point 3. So at this point, you would just do the negative log of the concentration of OH minus to find the pOH, and then you would use the rule where you can do the 14 minus pOH equals pH. Let's look further at the titration and test ourselves by asking, what form is the acid in at our different points throughout the titration? So starting with point 1. At point 1, we only have the weak acid, so most of our acid is not dissociated, so it's pretty much all just HA. Let's skip point 2 and go to point 3. Once we reach point 3, all of the H has been taken off of HA, so now we're all A-. During the whole time in point 2, our HA concentration is going down, and the A- concentration is going up. And exactly in the middle between point 1 and point 3, so if point 1 started right here, point 3 was around here, then find the middle point on the x-axis, go up, and on that point, we have added half of the amount of OH as we started with of HA. So if we have neutralized half of HA, then that means that half of it turned into the conjugate base and half of it is still HA. So now A minus and HA concentrations are equal. And then past point 3, like what we already talked about, all that's happening is the OH is just staying in solution and increasing the concentration of OH. Now finally we can talk about how to solve for the pH here, and we're going to look at how this graph can be used to show you the pKa of the acid. So I'm going to zoom out so we have more room to work with. First, let's look at the pH. To find the pH, you need to first find the equivalence point. And the equivalence point is whenever we added enough OH to totally neutralize HA. And remember, we said that was at 0.3. Now what you need to do is calculate how much OH was added to get to 0.3. So now trace a line down to figure out how many milliliters of NaOH were added, and you'll see that it's about 70 milliliters. So now you want to think about how many moles of NaOH were in 70 milliliters, because that will be equal to the number of moles of the acid, because we know that at this point all of the acid has been neutralized. So you would do 70 times 10 to the negative 3 liters times 0.1 moles per liter, because in the problem we're told it's a 0.1 molar solution, so 0.1 moles per liter, which gives us 7 times 10 to the negative 3 moles. The HA and the OH reacted in a 1-to-1 ratio, so that means that there are 7 times 10 to the negative 3 moles of the acid as well. That was in a 1 liter solution, so that means that the molarity is also 7 times 10 to the negative 3. So your final concentration of HA in the original solution is 7 times 10 to the negative 3 molarity. Now the final thing we need to look at is when you look at point 2 is really important, so point 2 on the graph, because this allows you to calculate the pKa. Remember at point 2 we said the concentration of A minus equals HA. And in the entire phase of number 2, we are going to use the Henderson-Hasselbalch equation to calculate the pH. So if we set up the Henderson-Hasselbalch specifically for just at point 2, we end up with pH equals pKa plus log of A minus over HA. At point 2, A minus and HA concentrations were equal. So if you look in the term for the log, if those concentrations are equal, then that means we have log of 1. And we're not going to look at how you solve logs right now, but log of 1 equals 0, so then that entire term can be crossed out. So then you end up with pH equals pKa. So halfway between your starting point and your equivalence point, that's called the half equivalence point. And at the half equivalence point, whatever the pH is, which we get from the y-axis, that will be equal to the pKa of that acid. So the pKa of an acid is equal to the pH that you get from a titration curve whenever you're at the half equivalence point. Now we're going to look at some common titration curves and break down the foundations of how you should be thinking about this. So if you see a titration curve that is not one of these situations, you should still be able to think your way through it. So let's start at the top left where we have a strong acid titrated by a strong base. At point 1, our acid is a strong acid, so it has totally dissociated. So that means that there is no HA left. And the pH is really low because it's a strong acid, so all that H plus is now in solution. And then post point 1, we start to add the OH, and the reaction that you want to imagine now is just OH plus H plus. And again, that's because there's no HA left. So the OH minus is just going to combine with that H plus that's in solution and start to create water. When we reach the equivalence point, what you need to recognize is that this is always going to be at a pH of 7, because when we add enough OH to completely neutralize the H plus that we got from the acid, all of that turns into water, and the only remaining ions in solution would be the anion from the strong acid, and this is a very weak base. And then the OH was brought from the Na plus most likely. So the only thing we have in solution besides H2O at this point is the A minus and the Na plus. Na plus is not going to react with water, it just dissolves in water. And then when you have a very weak base, due to the fact that this was a strong acid, it means we have an extremely weak base. Then that weak base is not going to be reacting with water in any significant way whatsoever, if at all. So pretend you have something like HCl, then your base, your conjugate base here is just Cl minus, which is not going to react with water at all. It'll just dissolve in water like sodium. So basically you're just left with H2O and then some salts in the water. So your pH is going to be 7 whenever you titrate a strong acid with a strong base. And then past the equivalence point, now we're just increasing the OH concentration, so the pH just goes up for as long as we continue to add OH. The strong base titrated by strong acid is pretty much the exact same logic, but you reverse it, where at the starting point, your pH is really high because your base has completely dissociated. So if we had something like NaOH, all of the OH dissociates away from the sodium, which will drastically raise the pH. And then as we titrate this with a strong acid, and let's just use HCl for example, the HCl would totally dissociate into H plus and Cl. So now our titrating reaction is the hydrogen ions combining with the OH ions, just like what we saw in the strong acid problem. And that's just creating water. So at your equivalence point, your pH will be 7. And it's the same reasoning. The only thing that's present besides water will just be Cl and Na. Or if it's other acids and bases, it's still going to be the same idea where you're basically just creating a salt inside of this water because the strong acid and strong base have such weak conjugate acids and bases that there's virtually no dissociation. So now let's look at a weak acid titrated by a strong base. Your weak acid pH starts a little bit higher than the strong acid one, just like what we talked about earlier, because it's a weak acid, so it doesn't lower that pH as much. We already broke down the weak acid titrated by strong base, so all I'm going to point out now is that the pH is a little bit higher than 7 at the equivalence point. And in the previous example, it may have looked like our pH was right at 7 at the equivalence point, and that's just more of a drawing error than anything. But the reason that your pH is more than 7 at the equivalence point, and again, reference the beginning of that video, remember we said that at the equivalence point, there is no HA left, and all of it is now A-. The conjugate base of a weak acid is significantly stronger than the conjugate base of a strong acid. So it's still not a strong base, so make sure you're not making that mistake. It's not a strong base, but it is strong enough to raise that pH a little bit above 7 because that conjugate base will be reacting with some of that water that's in solution in just a normal weak base problem, which causes the OH concentration in solution to go up a little bit. And then as we continue to add OH past the equivalence point, the pH will just rise because the OH concentration is rising because nothing is neutralizing it. And lastly, the final one with the weak base titrated by strong acid. We won't go in depth about this because the logic is the exact same as the weak acid one, but you just need to be thinking about it from the perspective of the base. And so let's just start with the equivalence point. At the equivalence point, our pH is a little bit less than 7. And hopefully you can kind of figure out why it is, but that's because at the equivalence point, there is no unreacted base left. So the concentration of the base is 0. And as we were adding H+, we were getting rid of the base by making it BH. So our reaction during the titration was B plus H+, and the H+ is coming from the strong acid, and that creates BH. So at the equivalence point, all of the original base has now turned into BH, and the conjugate acid of a weak base is a weak acid. So then BH, because it's a weak acid, will partially react with water in a regular weak acid problem, which will slightly increase the hydronium ion concentration, which lowers the pH. So that is why at the equivalence point, your pH is a little bit lower than 7 whenever you are titrating a weak base with a strong acid. So again, think through the foundations of this, and then that way if you're given a type of titration that we did not go over, you'll still be able to think through it. With the polyprotic titration, there's nothing new in terms of the concepts we'll apply, but it's just applying it to a little bit harder of a problem. So at the beginning, so at point 1, this would be H2A reacting with H2O. And if this is a strong acid, then it'll totally dissociate. And then you would calculate your pH by just finding the concentration of the original H2A. And then if it's a weak acid, you would do an ice table like we just said. And there was a video, the previous video talked about the difference between a polyprotic weak acid and a polyprotic strong acid. So depending on which one it is, that will determine how you find the pH at the very beginning before the titration has begun. We're going to proceed forward like this is a weak acid. So just keep that in mind that yes, a strong polyprotic acid would be slightly different, but generally you're going to think about it pretty much the exact same, but we're going to just talk about this like it's a weak acid. So at point 2, as we've started to add OH, the OH is reacting with the unreacted H2A because remember it's a weak acid, so barely any H2A dissociated in the beginning. So from point 1 to about right here would be point 2, and hopefully you can spot this, but to calculate the pH during point 2, that is going to be the Henderson-Hasselbalch equation. And then once we have reached the middle of that steepest point, we know we have reached the equivalence point. So at this point, all of the H2A has reacted with the OH that we added. And we call that the first equivalence point. And then at this point, all of the H2A is gone and it's all HA minus. So at that first equivalence point, point 3, you could calculate your pH by just doing a weak acid problem using HA. And then from this point, we continue to add OH, which then reacts with that weak acid HA. So point 4 would be basically the equivalence of point 2 for the first proton. So point 4 is OH reacting with the second proton. And during that range of point 4, you again use the Henderson-Hasselbalch equation to calculate the pH. And then we have a second equivalence point. So that is once all of the HA has now been reacted. And then any point past that, you're just adding OH and it's not reacting with anything. So now you need to be using the concentration of OH to find the pH. And at that second equivalence point, everything is A minus. There's no HA and there's no H2A left. So again, it's all the exact same concepts except we have 2 equivalence points now. And that means we also have 2 half equivalence points. So at these 2 points, so I'll just put a yellow 1 and a yellow 2. At that first part, that would be the first half equivalence point. At point 2, that's the second half equivalence point. And again, remember your Henderson-Hasselbalch equation. And at the first point, we have pH equals pKa. And remember, that is pKa 1. So that's the pKa for that first proton. So pKa 1 plus log of the conjugate base for the first acid. So that is HA over H2A. And then again, that log will be 0. So the pH at point 1 is equal to the first pKa. And then that exact same logic applies for the second equivalence point. But remember, at that second equivalence point, our acid is now HA. So pH equals pKa, and then use the second pKa. And then plus log, make sure you now use the correct conjugate base, which would be A minus. And then use the correct acid, which would be HA. And then once again, the log term would cancel out because when those concentrations are equal, the log equals 0. So at the second half equivalence point, your pH is equal to pKa2. And see if you can think through how this would work if it was a strong acid, but just to give you a hint here, at point 2 and at point 1, we don't have any H2A because if it's a strong acid, it completely dissociates. So you would need to calculate the pH how you would whenever you have a strong acid at point 1, and then at point 2, your reaction would not be H2A combining with OH, it would be the H plus reacting with the OH. And we talked about that just briefly when we looked at the strong acid being titrated by the strong base, but just make those adjustments and then the logic is still the same throughout. But notice that you would not be using the Henderson-Hasselbalch equation because that requires that you had a weak acid and a weak base, and you would need some significant amount of H2A to use the Henderson-Hasselbalch equation. So all you're going to be doing to calculate the pH while the titration is occurring for the strong acid part is just calculating the change in the H plus concentration. And then once you hit the second proton, where now you have a weak acid, even if the first proton was a strong acid, the second proton is going to be a weak acid. Now you're back to the same logic that we just used for the other titration.